Welcome back to the Deep Dive. Today, we're really going to dig into what might be the single biggest performance headache in generative AI right now.
Yeah, it's something everyone using these models feels.
Exactly. We hear all about the massive compute for training LLMs, right?
Yeah,
That gets the headlines. But the real sort of day-to-day engineering challenge now is inference. It's actually using the model.
it really is. The hardware focus, you see, it's shifted. Training, that's about massive data parallelism, throwing huge batches at GPUs, which they handle well, pretty well.
Okay.
But inference, especially real-time generation, that's autoregressive. It's one token after another sequentially. And that sequential nature, it just breaks the standard compute model.
And that brings us to the attention mechanism,
Yeah.
and specifically its huge memory footprint for the KV cache, key value cache.
That's the one. The attention bottleneck.
So this deep dive is all about that bottleneck and maybe a pretty radical hardware fix that tries to kill off this problem of just shuffling data around constantly.
Yeah.
Okay, let's unpack this. What exactly makes attention such a nightmare for the hardware we have now?
Well, the core issue is that autoregressive process itself. To predict the next word or token, the model basically needs context. It needs its history.
The whole conversation up to that point.
Pretty much, yeah. And if you had to recalculate the influence of every previous token for every new token from scratch, I mean, it would be incredibly slow, unusably slow.
Right. Okay, so caching is the obvious optimization.
Precisely. You store the results of some intermediate calculations, the key and value projections for all the previous tokens. That's your KV cache.
Stops the recomputation, great.
But it swaps one problem for another. You go from being compute-bound, maybe, to being intensely memory-bound.
And this is where the standard GPU design kind of falls down.
It's an architectural mismatch, really, rooted in how chips are built. That KV cache, it gets big. You mentioned Mistral 7B. That can be like 8 gigabytes. Easily.
Wow.
And on a normal GPU, that huge chunk of data lives in high bandwidth memory, HBM. It's high capacity, but it's relatively slow, and crucially, it's off-chip. It's physically far from the compute units.
Far in chip terms, anyway, like across the street versus in the same room.
Exactly. So for the attention calculation to happen for every single new token, that entire multi-gigabyte KV cache has to be hauled from the HBM across the memory bus into the tiny fast on-chip SRAM where the math actually happens.
That sounds painful.
Uh-huh.
Especially, like you said, for inference. If you're generating tokens one by one, say, in a chatbot, batch size of one, there's no other work happening to hide that delay, right? The processor just sits there.
It just waits, waiting for gigabytes of history data to travel across the chip just to predict the next few bits of a word. And the latency floor this creates is bad enough, limiting your tokens per second.
But there's more, isn't there? The energy cost.
Oh, the energy cost is the real kicker. Moving those gigabytes back and forth again and again, token after token, it consumes vastly more energy than the actual matrix multiplications doing the attention calculation.
Seriously. More energy moving than calculating.
Significantly more. This HBM to SRAM data transfer isn't just a latency bottleneck, it's an enormous energy hog. It dominates both speed and power consumption for generative LLMs in practice.
So, okay, tweaking algorithms might help a bit, shrink the cache size maybe, but it doesn't fix the core issue. You're still moving too much data too far.
Exactly. If you want, like, orders of magnitude improvements, 10x, 100x more, you can't just optimize the current way. You need a fundamental shift. You have to move the compute to the data.
Which brings us to in-memory computing, IMC.
That's the paradigm shift we need. The basic idea of IMC is elegant. Stop shuttling data to the processor. Instead, do the math right inside the memory cells themselves.
Using physics, right, like Kirchhoff's law. Apply voltages on the rows, currents sum up on the columns, and boom, you've done a multiply-accumulate operation.
Pretty much, yeah. It's clever physics. But there's a catch when you think about LLMs.
Okay.
A lot of the IMC research you hear about uses non-volatile memory, NVMs, things like ReRAM or phase change memory. And these are actually pretty good for storing the static weights of the transformer, you know, the fixed parameters and the linear layers that don't change after training.
Right. Those are constant. But wait, the KV cache is the total opposite. It changes with every single token. New keys and values are constantly being added, and sometimes old ones dropped.
You've hit the nail on the head. How do you handle that constant rapid overwriting? NVMs are generally slow to write, they take a lot of energy to write, and they have limited write endurance they wear out.
So NVM-based IMC is great for the stable parts of the model, but totally unsuitable for this super dynamic KV cache.
Exactly. They're just not built for that kind of churn. This specific problem demands a different kind of memory, a custom solution.
Yeah.
And the sources point to something called charge-based gain cells.
Gain cells. Okay, sounds specialized. What makes them the right tool for this job?
Well, think of it as a clever bit of analog engineering. A gain cell stores its value as an analog voltage on a tiny capacitor. Simple enough. But the key innovation is how you read it. It uses a push-pull transistor pair.
Okay. And that lets you do what?
It enables a non-destructive read. You can check the voltage on the capacitor, read the stored K or V value multiple times in parallel even, without draining the charge or disturbing the stored value.
I see. Unlike some simpler capacitor memories where reading it basically erases it, that's critical if you need to use those K and V values multiple times in the attention calculation.
Absolutely critical. So these gain cells are fast to read and write. They're low energy, they have very high endurance, which you need for that constant updating, and they naturally handle analog values. Plus, and this is big for Bensity, they're suitable for monolithic 3D integration, stacking layers of memory vertically.
Wow, okay. So purpose-built memory for a purpose-built problem. Now, how does this fit into the overall chip architecture? The goal was fully analyzed attention, right? And crucially, no ADCs.
Right. Avoid analog to digital converters wherever possible. They are notoriously power-hungry in mixed signal designs, so the architecture maps the whole attention calculation onto two main arrays of these gain cells.
Two arrays.
The first array holds the key vectors, the Ks. It takes the query vector, Q, as input, computes the dot products, and outputs the raw attention scores, S, all in analog.
And the second array.
That one stores the value vectors, the Vs. It takes the activated scores, we'll get to that as input, performs the weighted sum, and outputs the final attention result vector, A. Again, all analog.
How do they handle the inputs and outputs between these analog stages, like the query vector Q?
Also clever, they use pulse width modulation, PWM. Instead of representing a value by voltage level, they represent it by the duration of a voltage pulse.
So a bigger value means a longer pulse.
Exactly. We're talking really short pulses, maybe up to 15 nanoseconds for, say, a 4-bit quantized value. Multiplication then happens in this analog time domain.
Okay, this is where the paper got really interesting for me. They got rid of the ADC using something called a charge-to-pulse circuit. And this little circuit does double duty.
It's the core innovation, really. First, yes, it replaces the ADC. It takes the summed analog current coming off the columns of the first array, that's the dot product result, S integrates it onto a capacitor.
Okay, collecting the charge.
And then it converts that amount of charge directly into the width, the duration of an output PWM pulse. So analog current in, time to pulse out, no digital conversion needed.
So it's like an analog to time converter. But you said double duty.
Yes. And this is brilliant. The physical way that circuit works, how the charge builds up and triggers the pulse, it naturally implements a specific mathematical function. They designed the physics to be the math.
What function?
A hard sigmoid activation function. This replaces the standard softmax function you usually see in transformers.
Whoa. So they didn't just replace the ADC, they replaced the softmax activation too. Why? Softmax is standard.
Because softmax is computationally expensive, especially in parallel analog hardware, it requires normalization across the entire sequence length. You need to know all the scores to normalize any one score. That's a global operation, a killer for this kind of parallel, local analog compute.
But hard sigmoid is local, right? It just depends on the individual input score.
Exactly. They traded the mathematical purity of globally normalized softmax for the massive efficiency gain of a local activation function that the hardware could basically do for free as part of the signal conversion. It's profound co-design.
That is cover. Trading perfect math for practical speed and energy. Okay, so how does this all flow together? They use sliding window attention.
Right, to keep the array size manageable and focus on recent history. They only attend to maybe the last M tokens, using the gain cell arrays like a circular buffer. The whole process for one token's attention step takes about 65 nanoseconds.
65 nanoseconds, that's insanely fast. How do they hide the right time? Doesn't writing the new key and value for the token just generated take time?
It does, about 10 nanoseconds for the value vector write. But here's the pipeline trick. That write operation happens in parallel with the next token's computation starting. Specifically, it's hidden behind the Q.K calculation in the first array.
So the writing is masked by the computing. The pipeline is always full.
Pretty much. Write latency gets completely hidden.
Okay, but analog circuits have limitations. Noise, voltage drops over distance, IR drop. You probably can't make one giant 1024 by 1024 analog array, right?
Correct. Practical analog array sizes are limited, maybe 64 by 64 in this design, due to those non-idealities. So to handle a larger effective KV cache size, like the 1024 needed for something like GPT-2's head dimension.
They tile it.
Exactly. They use, say, 16 identical smaller subtiles, each handling a 64-token chunk of the history. Each computes a partial attention result in parallel in the analog domain.
And then combine those partial results.
Yes, and this is where the hybrid part comes in. Those 16 partial analog results are combined accurately using a tree of standard digital adders. So you get the massive efficiency of analog for the core multiplication, but the robustness and scalability of digital for summing up the final result.
Makes sense. Best of both worlds.
Yeah.
But this whole system sounds very different from ideal digital math. You've got hard sigmoid instead of softmax, quantized values, capacitor leakage maybe, PWM signals, and you mentioned the gain cell multiplication isn't perfectly linear either.
All right, the paper models it as a third-order polynomial. It's non-ideal.
So what happens if you just take a standard pre-trained digital model like GPT-2 off the shelf and try to load its weights onto this messy analog hardware?
Utter disaster. Performance completely collapses. The model outputs gibberish. Perplexity, which measures model confusion, goes through the roof. Because the weights were trained assuming perfect digital math, not this analog reality.
And training a model from scratch while simulating all these complex analog effects would take forever and be super inefficient.
Yeah, exactly. Not practical. So they needed a clever way to map the knowledge from the digital pre-trained model onto this non-ideal hardware. A two-stage process.
Stage one.
Divide and conquer. First, they created an intermediate hardware model. This model simulated almost everything, the hard sigmoid, the quantization, the array structure, the pipeline, but it pretended the core gain cell multiplication was perfectly linear.
Ignoring the messiest part for a moment.
Right. They then fine-tuned the public GPT-2 weights on this slightly idealized linear multiply hardware model, and it worked remarkably well. They reached the baseline GPT-2 performance level in fewer than 3,000 fine-tuning iterations, way faster than training from scratch.
Okay, so transfer learning works if you ignore that final nonlinearity. But you can't ignore it in the real hardware. Loading those fine-tuned weights onto the actual nonlinear hardware, that's when perplexity shot up to 1,757.
That's the catastrophic failure point. The nonlinear multiplication breaks everything.
So stage 2 has to fix that. And this, you said, was the real aha moment. No complex retraining.
This is the coolest part, I think. They developed a novel, gradient-free adaptation algorithm. No backpropagation, no calculus needed here.
Gradient-free? How?
They basically insert very simple linear scaling operations. Think Monterey, Uplex plus Beadball at strategic points after the nonlinear analog computations.
Just multiply and add.
Yeah.
Seriously. How does that fix a complex nonlinearity problem?
It's about statistics, not calculus. The goal isn't to retrain the weights in the deep learning sense. The goal is to make the statistical distribution of the signals after the messy analog step match the distribution of the signals in the well-behaved linear model from stage 1.
Wait, so they just adjust A and B iteratively until the average value and the standard deviation, sigma of the activations, look the same in both models.
That's exactly it. They're not forcing the individual values to be identical. They're forcing the overall statistical profile of the signals to match. It's purely statistical calibration.
And that worked. Just matching mean and standard deviation.
It worked astonishingly well. This simple gradient-free statistical tweak brought the perplexity down from that disastrous 1,757 all the way to 21. Basically recovering the original performance.
Without any gradient descent. That's wild. And incredibly pragmatic. It proves you don't always need perfect math. You just need the signals to behave statistically like they should.
Precisely. Preserve the statistics, preserve the performance. It's a powerful technique for bridging the digital analog gap.
Okay, so let's get to the payoff. All this clever co-design, the gain cells, the ADC-free path, the statistical fix. What are the final performance numbers? Keeping in mind this is just for the attention part of the model.
The numbers are pretty staggering. Latency per token is around 65 nanoseconds, compared to a top-tier GPU like the NVIDIA H100, which takes maybe 6.5 microseconds for the same task. That's a 100x speedup.
100x faster than an H100. Wow. And compared to, say, embedded GPUs?
Compared to embedded GPUs, it's more like 7,000x faster. It's practically instantaneous attention.
Okay. Speed is one thing. What about energy? That was the other huge bottleneck.
Energy savings are even more dramatic. The total energy for processing one token through 12 attention heads is about 73.2 nanojoules.
Nanojoules, how does that compare?
Compared to the H100, it's roughly a 70,000x reduction in energy per token. Compared to something like an RTX 4090, it's closer to 90,000x less energy.
70,000
Yeah. Yeah.
times more energy efficient. That's hard to even picture. It's like comparing a car's fuel tank to a camera flash.
It's that level of difference, yeah. It fundamentally changes the energy equation for inference.
And what's interesting is where the tiny bit of energy it does use actually goes.
Right, the breakdown shows that the majority of the energy, about 58%, isn't even used by the analog gain cells doing the computation. It's used by the supporting digital logic, the control signals, the routing, those digital adders for combining results.
The analog compute became so efficient that the digital overhead is now the main power draw. That's usually a sign you've successfully accelerated the target function.
It's a classic signature, yes.
And critically, all this speed and efficiency didn't ruin the model's accuracy. The final hardware-aware model performed as well as the original software GPT-2.
Yes, on standard NLP benchmark tasks, the final adapted and fine-tuned model achieved comparable accuracy to the baseline software GPT-2. It validates the whole end-to-end co-design process. Plus, it's compact, about half a square millimeter per head, with potential for even more density via 3D stacking.
So boiling it all down, the key breakthroughs were:
I'd say three things. One, using the right memory, those specialized gain cells, specifically for the dynamic KV cache problem. Two, the ADC-free design, especially using that charge-to-pulse circuit to both convert the signal and implement the activation function physically. And three, that really pragmatic software-to-hardware mapping, particularly the gradient-free statistical adaptation to handle the analog non-idealities.
And where this fits today, it's not a full replacement for a GPU, right?
Yeah.
It's more like a specialized coprocessor.
Exactly. Think of it as an attention engine or an accelerator. You'd pair it with a conventional processor or maybe other IMC blocks. Its job is to handle the attention mechanism, offloading that massive memory bottleneck from the main system.
So the next logical step would be
Combining this dynamic gain cell approach for attention with, say, static NVM-based IMC for the other big part of the transformer, the MLP, or feed-forward layers, which use static weights. Build a heterogeneous chip.
mixing and matching the best IMC for each part of the model.
That seems like the path toward a complete ultra-low power inference engine on a chip.
It really highlights a fundamental trade-off, doesn't it?
Yeah.
This whole design works by deliberately sacrificing mathematical perfection, giving up linear multiplication, giving up global softmax to gain these absolutely massive 70,000x improvements in hardware efficiency. Perfect digital math was the enemy of practical speed and power.
It really was. And that brings us to a final thought, something for you listening to consider. Maybe the future of AI hardware isn't just about building faster, more perfect digital processors. Maybe it's increasingly about designing smarter software algorithms, calibration techniques like the statistical adaptation we saw that can effectively compensate for the unavoidable imperfections of massively efficient but non-ideal analog hardware.
So the challenge shifts from just building better silicon to building software smart enough to make imperfect silicon perform brilliantly.
Could be. The next leap in LLM efficiency might come not just from the hardware engineers, but from the people figuring out how to make algorithms thrive despite the hardware's flaws.